this is Chapter 1, Section 7, AP Chemistry, and we're going to talk about significant figures. So there are 3 rules that you have to memorize for significant figures. Number 1, anything that's not 0 is significant. So 1 through 9, all those digits are significant. Number 2, trailing zeros, that means on the right side of a number, so anything to the right of a number is going to be trailing. Those are significant if they follow a decimal. So trailing zeros after a decimal, it has to meet both of those criteria. It has to be on the right of a number and it has to be after a decimal. Those are significant. And then all zeros in between significant digits are significant as well, and that's the sandwich rule. When you add or subtract measurements, you are going to use the same number of digits after the decimal point as the one with the fewest. So if you were adding 1.5, let's write that up here, or down here, I should say. If you were adding 1.5, and you are adding 0.25, then you would get 1.75, right? But that is not our final answer, because we have to look at which measurement had the fewest number of decimal places and round to that number of decimal places. So this has 2 decimal places, this one just had 1. So our answer needs to be rounded to this 7. So I'm gonna mentally draw a line here, and anything to the right of that line, if it's 5 or greater, we round up. If it's less than 5, we round down. So this is going to round to 1.8, and that would be my final answer. Okay, so that is a little bit different than what we normally use, because usually in chemistry we are multiplying or dividing. When we add or subtract, a really good example would be when we're using a burette. So if you're reading from a burette, which is that long skinny instrument that the liquid comes out of, and you add it into a flask at the bottom, we usually use it for titrations. So as it goes down, you're going to take your initial measurement and subtract the final measurement, and you're going to see how much it decreased by, how much left the burette and went into your flask. And when you subtract that, you're going to find that you have to look at the decimal places. Okay, first of all, you have to read from the bottom of the meniscus, right, the rounded part of the liquid. You read from the bottom of the meniscus, both measurements, you're going to subtract and make sure that you look at how many decimal places you started with. That's how many you should end with. Okay, multiplication and division, personally, I think is easier. If you're multiplying and dividing numbers, then all you have to do is find out which one has the fewest sig figs, and that's how many you round your answer to. Okay, so let's do some examples. How many sig figs are in each of these numbers? So I will underline the significant figures. Anything that's not 0 is automatically significant. This is a trailing 0 because it's on the right of the number, and it's after a decimal, so this 0 is also significant. Okay, not 0, significant. These are trailing zeros, but they are not following a decimal, so those are not significant. So there's just one significant figure here. Okay, all of these non-zeros are significant. These are trailing zeros. They're on the right side of the number, and they follow a decimal, so these are also significant. So this has 6 significant figures in number 3. Excuse me. Non-zeros. And this is the sandwich rule. It's sandwiched between the 8 and the 7. So the 0 is also significant. So this one also has 6 sig figs. Okay, this is a really long number. And we have 2, 3, 5 non-zeros. Sandwich rule. These are sandwiched between sig figs, so these ones count. And this is a trailing 0 to the right of a number, and it is after a decimal, so this one also counts. So we have 1, 2, 3, 4, 5, 6, 7, 8 significant figures in number 5. Let's get rid of these. Okay. Looking at the next problem, I have 2 non-zeros, and I have 2 trailing zeros that follow a decimal. So I have 4 significant figures right here. In this problem, there's only 1 non-zero. These 2 are trailing and they follow a decimal. And because these are now significant, this is sandwiched between significant figures. So this one's also significant. So this one has 4 significant figures. Non-zeros, zeros that are trailing the number and they follow a decimal. This one has 4 significant figures. And these are my non-zeros. These zeros are sandwiched in between. This one has 5 sig figs. And last but not least, this is non-zero. This is trailing, and it's not following a decimal, so it does not count. So number 10 only has 1 significant figure. Really quickly, we say trailing. If there a 0 was added here, that would be really weird. You don't say 040. But if you put a 0 there, no zeros on the left of the number are significant. Okay, so that's why we're only worried about trailing zeros to the right of a number. All right, accuracy and precision. So accuracy is how close a measurement is to the accepted value. In chemistry, we have measured the density of aluminum. What we should have got, I believe, is 1.79 grams per milliliter. And what we usually get is just slightly less than that. So let's say we got 1.75. How close we are to that actual accepted value is our accuracy. Precision is how close together a set of numbers are. So if we did that many times, which you guys know in a lab, we want to do as many trials as possible to get reliable data. So if we were to repeat that lab many, many times, and we have numbers like 1.7, 1.6, 1.71, 1.8, those are fairly precise. They're pretty close together. Sometimes groups will do it and they'll use different balances for each trial because this one's being used, so they just pop over to the next one. Well, if they're not calibrated the same, you might get numbers like 1.7, which is pretty good, 2.4, or 1.3. If they're all over the place, then that is very imprecise. Okay, that is not good. And we have 4 scenarios here that show accuracy and precision. So for this one right here, we have both accurate and precise data. So if we hit the bullseye over and over again, all of our trials lie in this middle area, then we are both accurate and precise. Okay, down here, if we are precise but not accurate, that means that our numbers are close together, but they're not what they should be. Okay, so like this little clump right here, if this was an actual bullseye in a darts game, you would say something's wrong with this person's glasses, or when they close one eye, everything shifts. There's something going on there, right? If they can hit it in the same spot every time, but it's off, something's wrong. Over here, this is not precise because you can see there's one way up high and there's one way down low, and then there's a bunch surrounding it. However, if you averaged all of these values together, then the error would average out and you would be pretty close to the bullseye. Okay, so the average of all of these would be pretty accurate. And lastly, this is neither precise nor accurate. These are all over the place. And if you average them all, you'd be off from the actual accepted value. Okay, there are 2 types of errors that I want you guys to think about. So we have random error and we have systematic error. Random error is error that has an equal probability of being too high or too low. So when we use a balance and the balance goes up and down, we might take the mass 5 times and find 5 slightly different numbers. That is random error. Okay, could be the way the wind was blowing on it, somebody stepped. Okay, so those small differences, those are random errors. They're hard to almost completely eliminate. We try to reduce them as best as we can because we want good results, right? We want to be accurate as close as we can to the actual value. But all measurements have some degree of random error. Systematic error, on the other hand, systematic error is going to be either too high consistently or too low consistently. And that has to do with something in the system is wrong. The procedure is telling you to do something incorrect, so you're getting the same result every time, but it's not what it should be. Another example would be if your balance is not calibrated and you're using the same one every time. This group might get 1.7, okay, 1.69, 1.70, 1.71. You might be getting 2.3, 2.4, 2.39. So while they're close together, something is off because your balance might be measuring things too high each time. Okay, so looking at these pictures, we can see which falls into which category. So which one looks like random error? This looks like it has random error in it, and this definitely has random error in it. Actually, this could have both systematic and random error and human error, which are just mistakes, which we try really hard not to make. And if we do make them, we try to correct them before reporting our final results. Okay, so this is random error. A little too high, a little too low. When you average them, they tend to go away and you're in the center. This is a classic example of a systematic error. There's something wrong with the system. So like our person throwing darts, when they close one eye and everything jumps and they're hitting the same spot, but it's off from the target, that's a systematic error.